Well, good afternoon. This is a presentation about database technology from the perspective of a software engineer who cares about, obviously, software engineering, but also about computer sciencey type topics. Before there was the iPhone, before there was the personal computer, way back towards the start of the kind of computing age, one of the very first things that people tried to do with computers was to build databases to help them store information and do interesting things with it. For me, I started working on and around a database system about 3 years ago. And at the time, I stopped being a hands-on programmer for the most part. I'd lost interest in it a little bit because I kept finding that projects weren't challenging, or when I was doing the work of a working programmer, that I didn't feel like I was learning. And for me, that's how my motivation works. If I'm learning something new, then I feel like I'm getting better and I'm happy. And if I'm not learning something new, then I feel like I'm a bit stuck. And that maybe explains why there's a lot of information in this presentation, because I'm kind of assuming that everybody's like me and really likes diving into these kind of things. Yes, when I started working on that database system, I hadn't been programming for a while. I'd tried lots of things to reignite my interest in my profession, which is something that I'd always loved. I tried going back to university and studying mathematics, and that worked for a while, and then it didn't. So what did I try after that? I tried going back to university again, and this time I studied business, and that didn't work at all. But then I started working on this database system, and I really, pretty well immediately found my old enthusiasm for programming and regained that sense of learning new things. And I think the reason why is because databases are hard. They're really hard. And maybe it's probably not just databases, any kind of very ambitious software undertaking. So I think of things like trying to build your own operating system or inventing a new programming language, that kind of thing. And what I like about them is that they're so hard that it's effectively impossible to do it from scratch. You can't start developing a database from first principles. It's just too difficult. There's too much to know. So what you do instead is you go back and you look at the history, and you dig into your favorite tools. You go find the source for Postgres, if that happens to be one of your favorite databases, like it's one of my favorite databases. And so this whole learning process gets underway, and you discover that there's all this great engineering stuff built into these database tools that we use. And some of it has been there from the very beginning. If you go all the way back to 1972, and System R, one of my kind of favorite database papers, they describe a lot of principles for implementing a database engine that are still present in the majority of database systems today. And that's pretty amazing. Of course, people have had new ideas in the last 50 years, and so the whole industry has moved forward and gotten better as well. So, clicker's not working because it's not plugged in. That's why. Okay. Oh, yeah, okay, I'll just kill that. Is it okay if I take that out? No. Sorry, I'm just plugging in my pointer. First up, let me introduce Wormwood. Wormwood is a bespoke database system developed specifically for this presentation. It's schemaless, it's read-only, it's SQL-like, but mostly it was developed with one goal, which is to be as simple as possible. And I don't really mean simple to use. In fact, it's a toy database. You can't do very much with it. But simple, for somebody who wants to learn about databases, you can look at the source code. The entire database is 660 lines of code. And as much as possible, I tried very hard to make it approachable and helpful from that perspective. So I'll do a demo of Wormwood. As I'm doing it, I want you to think about if you decided to build a system that was like this, it could do what Wormwood does, how would you go about implementing it? Wormwood is implemented in TypeScript. I chose TypeScript because it seemed like the most universal programming language that would make the tool accessible to the largest number of people possible. And because it's TypeScript, it runs on Node, and we start it with NPM. When it starts, it prints a little bit of help text for you. And so it's a read-only database. It has data in it already, and what we can do is we can query it. Because the talk's only an hour long, that's what I limited it to. We can do things like the SQL select statement to run a query against a data store. I can specify the properties that I'd like to retrieve from the data store. The source I'll be using is FIFA, so it's a collection of data about soccer players. And if we don't want to retrieve the full data set, we can use a where clause to restrict it. And I will restrict it to players where the age is equal to 41, because that's how old I am. So it turns out there's still quite a few players in FIFA at that age. So I know that that's obviously very impressive already, but we can do even more. Thanks. So if you wanted to order that result set, it supports the SQL order by. So I'll order by name in descending order. Okay, so that's done that. And finally, the last trick that Wormwood has is it implements a single aggregate function, which is mean. So I can select the mean age from FIFA. The average age of players in FIFA, quite a bit younger than 41, it's about 25 and a half. So that is Wormwood. And as we kind of work through the rest of this presentation, this is the example that we'll keep returning to in terms of how did I put together this database. The data format that Wormwood uses looks like this. So we have each data source is a text file, and each record in the data source is a line in that text file, and it is a JSON object. It's a bunch of keys and a bunch of values. So the FIFA data file that I queried before looks like that. Okay, so here we have a classic SQL select statement. SQL is a data querying language. So we can think of it as a function that gets applied to some particular data store at some particular instant in time to produce a particular value. So given the same query and the same state of the data store in that instant, we should, generally speaking, get the same result back. And we can also think about it as a process of applying a number of transformations to the data store in an order to get to our particular result. So it's not that everything happens all at once. As a programmer trying to come up with a query that produces the result that I want, it's helpful to me to be able to think about that kind of ordered series of things happening to get me incrementally towards the correct result. The only trick with SQL is that the syntax is mixed up. It's in the wrong order. If we were to order it in the logical sense, the from part would come first. because the very first thing we need to do in a sort of data pipeline sense is identify which data set we want to query. Having done that, we'd want to restrict the data that we're looking at. So we would have the where clause. So here we're querying a data set of living things, and we're filtering that down to the ones where the kingdom is equal to animal. And then finally, what do we actually want to do to that new data set to get our answer? And in this case, we're just going to count the set of rows. So as a programmer trying to write this query, it's helpful for me to be able to think through in that kind of order. But it turns out that as a programmer trying to actually implement the database engine to apply this query to a data store, it's also helpful because we can take that same pipeline approach of incrementally applying operators to our stream of data to get us to a final solution. This is called a data flow pipeline, or sometimes a data flow graph, depending upon your implementation. And if we look at that same query again, we start with the from clause, from the living things. And what we're going to do is take each piece of the query process and represent it as a node in the graph that applies one particular operator. So each of the different things we can do in our SQL query, we model as these operators with very specific jobs to do. So the first one we start with is a node that's of the data source type. And its job is just to produce values from the underlying storage. As you can see here, that's what it's doing. It's producing values of different type. But our query was restricted to the records where kingdom is animal. So then we need to add another node to our pipeline, and this one is going to be a filter type of node, which is responsible for implementing the where clause for our SQL select statement. So the filter node, it receives records from its input, which is the living things data source, and then it restricts it down to the records that satisfy its predicate, kingdom is equal to animal. Then we have a count operator, so it's another node added to the end of the data flow pipeline, and whatever input it receives, it just counts the rows and produces a value. So here we get to our final answer for this query, which is 2. So then the whole process is about building a graph of operators that each apply one little change in an ordered sequence to get us to the final result that we're after. And the way that I've depicted this here, it looks like a push-based system where the data source is starting things off by pushing things through a streaming process. But it's not actually how it works, it's the other way around. It's a pull-based system. Each of the nodes in our data flow pipeline is called, it's a thing called an iterator, and this design is known as the iterator model. And what it means to be an iterator is that you have some method, here in this example it's called next, but some method that when called produces a row. Either it can produce a row or a special value that says that there's no more data. So each of these nodes is an iterator, so they each have a next method that when called produces a row. So to actually evaluate the query, the client calls the next method on whichever node is at the top of the data flow pipeline. In this case, it's a count operator. And what count knows how to do is count a bunch of rows. So to do that, the first thing it's going to do is call the next method on whatever its input node happens to be. And because it's a counter, it's going to call that next method repeatedly until it gets the special marker that says that there's no more data, and then obviously it can count them and produce a result. However, when the next method of the filter node is called. The filter's job is to pull rows from its input, test its predicate, and only return rows where the predicate evaluates to true. So the count node calls the filter node, and then the first thing that it has to do is call the next method on the data source. And that one's simple. It's just going to return a row. The filter will check that row. If it's true, it'll return it up to the count, and that process gets repeated until there's no more data, and then we can we have our final result. This design pattern is called the iterator model. Within Wormwood, it's implemented as this interface iter. For a thing to be an iterator, it must implement iter, and iter has a next method. The return type of the next method is a row or end of file. In the Anatomy of a Database System, which is a really great read about all of this kind of topic, the authors provide this pseudocode for an iterator class. You can see that it has a constructor which accepts an array of inputs, and it has a method getNext that returns a tuple. A tuple is the same thing as a row. So this is just two versions of the same thing, that iterator model. Given that evaluating a query against a data store involves assembling the data flow graph and then calling the next method to cause the evaluation of the answer, the read side of a database then really becomes a process of building that data flow graph. That's the whole game on the read side. So we start with a user. The user has a query which they provide through some sort of interface. For Wormwood, it's a console app. And this is the query that I demoed. Select name and age from FIFA where age is equal to 41. So on the read side of a database, the first thing that happens is that query text goes into a parser module. The parser, it knows about the syntax of the language that we're working with, in this case SQL. It doesn't know anything about how our database engine is implemented. It doesn't know how to evaluate queries. It just understands syntax. And its job is to convert what it receives, which is an ordered list of characters, into some kind of internal data model that the rest of the application can work with. In Wormwood, that internal data model that is a representation of the query looks like this. So it's got a property to tell us that this is a select statement. It's got an array of fields that we need to pull from our data source. It's got a source property, so we know what we're querying, and it's got filter property and filter value, so we can restrict the data set that we're working with. But that data model and the SQL query, they're isomorphic representations of the same thing. We could easily convert this back to the SQL statement and vice versa. It's just a format that's more friendly for the rest of the system to work with. And speaking of the rest of the system, the next step in the pipeline is the planner. The output from the parser becomes the input to the query planner. And unlike the parser, the planner does know how our database system evaluates queries. It knows about the internals and how we're going to convert our query into a result. So the planner's job is to convert that query object into a query plan. Wormwood's query plans look like this. And the query plan is a description of the data flow graph to build. For this query, select name and age from FIFA where age is equal to 41, we need two nodes in our data flow graph. We need a producer, which can read records from the disk. And we need a filter, which can apply the where clause and restrict the data set. Each of those steps has associated metadata, which is what they need to be able to do their job. The producer can't produce records unless it knows which data source we're querying and which properties we want. And the filter can't apply the where clause unless it knows which property to check and which value it's looking for. So then the query plan becomes the input to the executor. And does anybody have any idea what the executor might do with that? Pardon? Yes, essentially, it gets us there because the executor, it takes that query plan and it builds the data flow graph. And once you have the data flow graph, then you just need to call the next method and you can get the result. Within Wormwood, this is like possibly the core function of the whole system because it's implementing that read side of the database. It's called evaluate. If you look at the signature of the function, the input is a string, which is the user's SQL statement, and the output is a promise of iter, which is our data flow graph. The first line of code takes our SQL statement and produces a query object. That query object is then given to the planner, the query planner module, which produces the query plan. And then the last line of the code, the executor takes the query plan and builds the data flow graph and gives it back to the client. Because the parser is the first step in that process, let's dive into that. Wormwood's parser is assembled out of parser functions. And if we were to define the type of a parser function in TypeScript, we would start with type parser, and it would have a type variable t, which is the value that this particular parser is able to produce from an input. Parser functions are functions from a string, which is our SQL statement in this case, and we want to parse out that value t. However, there's a problem. When we apply any particular parser function to any particular user input, we may or may not succeed in parsing a value. So actually our return type has to be t or null, which is fine, but also when we apply a parser function to some input, our parser may be able to parse the entire input, and in which case the job is done and that's great. But very often we just kind of parse a little bit and then the rest is left over for further parsing. So actually our return type has to be a tuple of some value of some type t or null and a string where that string is the remaining input that's left over from the parser. If you're not familiar with this syntax, the array syntax here is how TypeScript represents tuples. It's just a way of returning a type that's a product of some other types. Then we could define a type for, say, an integer parser if we wanted to be able to parse a number out of a string, and it would look like this. So the type of an integer parser is a function from a string to a tuple where the first value is either a number or null, and the second value is a string. So the only thing that's actually changed here is that our type variable t has been made into the concrete type number. Okay, so in terms of what that actually looks like, let me get my cursor on the right screen. This is some TypeScript code. The first line of code we have here is exactly what I had in the slide. So we've defined a type for a parser of some value t. And then I have an implementation of a parser for integers. The first thing to look at is just a few examples of what this does. So down here, we apply the int parser to the string 123 space foo. And then a second example, we apply the int parser to the string foo123. Now, if I run this, applying an int parser to 123 foo, it is able to see the numeric characters at the start of the string, and that gets converted into the number, 123, and then the string part that's returned is space foo. So we've consumed the first 3 characters, and then that's the bit that's left over. If we apply the int parser to the string foo123, then we're not able to successfully parse an integer out of that, so the value is null, and the remaining input is the entire string. So that's what they look like. Now, we can also visualize these parser functions like this. The function is the blue shape there. You can see that there's a string, which is the input, and the parser produces some value of some type t, and a string, which is the remaining part of the input. The really cool thing about this is that that string output from one parser is exactly what we need to connect into the input of a second parser. So we have a ready-made way to assemble a bunch of these parser functions, each of which does a very simple thing, but then when we put them together in the right way, we can parse more sophisticated syntax, such as the SQL statement. And the other thing about it, when you zoom out and look at something like this as a whole, you notice that this whole thing also has the same shape, that the parsers that we've glued together as a whole, they also have a string as an input. They also produce a value. Here it's t and t2, and they produce a string, which can become the input to another parser. So this is how we're able to compose parsers together to do interesting things. Because Wormwood is designed to be as simple as possible, its parser is also as simple as possible. So whilst it does use these kind of parser functions, the way that it joins them together is very basic. It just applies them sequentially to the input. The parser functions are represented here as these pacmen. So we have a list of different type of parsers that are all queued up in the correct order. When we go to parse the user's select statement, this select parser gets applied to the input. It knows how to parse the select keyword, so it consumes that part of the input, and it's produced a result that tells us that this is a select statement. The field parser knows how to parse a list of fields, so it does the same thing, consumes the input, produces a list of fields. The source parser is applied, and it consumes from FIFA and tells us that FIFA is the data source that we want to query, and then the filter parser can parse our where clause and add those values. So we end up with this query object. In code form, in Wormwood, this is the query parser function. So it's a function from a string, which is the user's SQL statement, and the return type is a query object. The user's query is input to the fields parser, which produces some values. The last value there, rest, that's the one that is the string that represents the remaining part of the query that's still to be parsed. So that then becomes the input to the next parser, which parses out the table that we want to read from. It produces a value, source, and it reassigns rest to the shorter input that's remaining, which becomes the input to the filter parser, which produces its values, reassigns rest again, and then same thing with the order by parser. And having done all of that, we're able to assemble it all together into the query object. That query object then is the input into our query planner, and the query planner produces this query plan. We have our producer step with its attached metadata, and we have our filter step with its attached metadata. In real database engines, the query planner is a very sophisticated component because it has two jobs. Firstly, it has to come up with a query plan that's going to produce the correct result. And secondly, it has to come up with a query plan that's going to be as efficient as possible. So there's a lot of optimization that happens in query planners. Not so much in Wormwood, it's very simple. But one thing that it does do in the query plan is it looks at the query and it looks at what indexes it has available, And if it finds an index that's going to make the query more efficient, then it uses that index, looks it up. The output from the query plan then becomes the input to the executor, and the executor converts the steps in the query plan into nodes in the data flow graph. So we have a producer node with its next method and a filter node with its next method. That then can go back to the client and gets evaluated into the correct answer. So to make all of this work, what you end up with is different types of nodes for your data flow graph. They all have a next method, but what they do in their next method varies significantly. So hence why I've included an example here. This is the source code for the filter iterator in Wormwood. Its job is to apply the where clause part of the SQL query. In its constructor, it takes another iterator, so that's its input. The fact that an iterator itself has an input iterator is what makes this into a graph. And it also has a filter step, which is the metadata that it needs to be able to do its job. It's an iterator, so it has a next method. Within its next method, the first thing it does is pull a row of data from its input. Assuming that it gets a row, it then uses its metadata to look up the property that we're filtering on and test it against the constant value. This one's looking at whether the age value is 41. If that expression is true, then that row gets returned up the chain. And if it's not true, then the filter pulls another row from its input and repeats the process until it runs out of rows. The next thing I want to talk about is complexity analysis. And this is important because so much of the database engineering topics, really, this is the stuff that they revolve around. And the job of complexity analysis, it's a branch of mathematics that aims to categorize algorithms by how the amount of work changes with respect to the size of the input. The syntax we use looks like this. So this is the complexity of an algorithm. We would say that this algorithm is order of 1, which means is what's called constant time. And it means that no matter how big the input or the problem is that you give to this algorithm, the amount of work always stays constant. If we were to draw it on a chart, it would look like this. You can see the size of the problem increases and the amount of work stays the same. An example of a constant time algorithm is looking up an element in an array by its index. If we have the index, excuse me, we can immediately jump to that element. So if the array has 3 items or 3 million items, it doesn't make any difference. The amount of time is always exactly the same. When talking about complexity, we also encounter this value n, which is it's a symbol that represents the size of the problem. Some algorithms are categorized order of n, which means that the amount of work grows at the same rate as the size of the input. A programming example might be some kind of loop that does something. If we loop twice as many times, it's going to take twice as long. So that would be a order of n type algorithm. When we think about database systems, this one is really very important, because if you have a data source and you want to find a particular record, the obvious way to do that, which is to search through incrementally, that's an algorithm that's order of n. If you look up a record in a database table without an index, then that's an order of n algorithm. If you double the amount of rows in your database table, then it's going to take twice as long. Some algorithms are order of n squared. This is called polynomial time. It looks like this when we chart it. So now you can see that as the size of the input grows, the amount of work curves around to the left, so it's growing faster than the size of the problem. An example of polynomial time is pairing all of the items in a list, or any time that you have nested loops over the same collection. Some algorithms are order of 2 to the power of n. This one is called exponential time. And the difference between these two, I've just swapped the position of the n and the 2. When the n is in the exponent position, it's exponential time. When we look at it, it looks about the same. So here I've plotted exponential time in blue. If I add polynomial time in red, you can see that after a while, the exponential time algorithm starts to increase more rapidly. So generally speaking, we would consider these algorithms to be worse or less efficient. So examples of exponential time algorithms is things like the calculation of permutations and combinations, and cracking a password would be one of those. Here I have a 32-character password. Each character is a Unicode character. So to check every possible password, I've got 150,000 to the power of 32, which is this many combinations that I have to check, which is a number with 165 significant digits. So exponential time algorithms can be dangerous. It's not all bad news, though. Some algorithms are order of log n, or logarithmic time. And when we look at the picture for this one, now the line is bending the other way. So it's better than exponential time, it's better than polynomial time, it's even better than order of n. Because as the size of the problem increases, the amount of work increases, but slower. And an example of an algorithm that's logarithmic time is looking up data based on an index. And that's where it becomes important for databases. Really, the entire job of a database index is to get us from order of n to order of log n. If we don't have an index, then we're down to a row scan, order of n. We have to search through sequentially. An index is a data structure. It includes entries, much like the index shown here from Programming Rust 2nd edition. Each entry has a key. In this index, the key is a term from the book, and entries have a value. The value in this index is the page numbers where that term can be found. And the entries are grouped and sorted. In a book index, they're grouped by the first letter, and then you can see within, say, G here, all of the entries are sorted alphabetically. So, say I wanted to find the term generic enums in Programming Rust 2nd edition. If I didn't want to use the index, then I would have to start at the first page or the last page, and I would have to check this page and this page and this page all the way through until I get to the end of the book, which is the worst case for us. If you imagined some kind of hypothetical Programming Rust book where all of the terms in the book were sorted alphabetically for us, then we'd be able to do better. If I wanted to find generic enums, I could split the book in the middle. I could look at the first term I see, closures. That's less than generic enums, so therefore I would know that the term I'm looking for is in the second half of the book. And from there, I would do the same trick, split that in half, look at the first term I see. If generic enums is less than that term, then my answer is in the first half. And if it's greater than that term, then my answer is in the second half. And that's binary search, and that's how we find things in sorted data. If we have an index, as we do in a book, then we can do better still. We can use the index to look up our value. And in databases, the structure that we use for indexes is typically a B tree, which looks like this. The values are grouped into nodes where within a node, the entries are sorted and values in between the values in a node get pulled down into child nodes. It's hard to explain. But as an example, if we had this B tree and we wanted to find the value 11, we would start at the root of the B tree and we would compare 11 to the first value, 7. 11 is greater than 7, so then we would compare 11 to 16. 11 is less than 16, so we would follow the pointer to the child node. 9 is less than 11, so then we'd move to the next value. 11 is less than 12, and there is no child pointer between 9 and 12. So at that point, we would know that the value 11 is not in this index. However many comparisons we had to do there, it's a lot less than working your way through the entire data set. Looking up something in a B tree index is order of log n. A curious little observation then is that the index in a book, like Programming Rust, is in fact a B tree index with a branching factor of 26 and 2 levels. The branching factor in a B tree is how many child nodes a node can have, and it's 26 in a book index because that's how many letters are in the alphabet. Binary search works on sorted data. B trees work with index data. Binary search is order of log n. B trees are order of log n. So if these two algorithms have the same complexity, does that mean that they perform the same? Well, someone shook their head. So in terms of like the mathematical perspective on it, they do have the same complexity. So as the size of the data set trends towards infinitely large, they will tend to perform the same. But in practice, as a person trying to build a database engine, they don't perform the same. And the reason why is because they have different bases to their logarithms. So a binary search is order of log n with base 2, and B-tree search is order of log n with base b, where b is the branching factor. So how many nodes a child in the B-tree can have, or how wide our B-tree goes. In real databases, they tend to have B-trees with extremely high branching factors, or several hundreds, or maybe into the thousands. So every time they check a node in the B-tree, they're able to massively shrink the volume of data that needs to be searched. So that's where they start to get much better performance than what you can get from a binary search. Okay. Wormwood has indexes, and this is what they look like on disk. So each index is a text file. It contains a JSON object. The JSON object has a property source, which tells us which data source we're indexing. It has a property called property, which tells us which property we're indexing. And then it has this lookup property, which for every value of the indexed property, it stores the line numbers where that value occurs. So where it says 17, these are the FIFA players who are 17, and each one of those numbers there is a line number of a player who's 17. So for example, if I looked in my FIFA data set on line 4,783, that player has the age 17. And of course, it has the same thing for every other age in the data set. Okay, so where's my query? That's my original query. Select name and age from FIFA where age is equal to 41. Evaluating that query at the moment, required 244 milliseconds. Wormwood has a stored procedure for creating an index. And we have to tell it which data set we want to create an index on and which property to index. So I'm indexing the age property on the FIFA data set. So Wormwood now has gone through that FIFA data set and it's built the index file, written it to disk. When we run the query again, this time when we get to the query planning step, I said part of that query planning process is to look for indexes that'll make the query more efficient. When it does that, it will find the index that we just created and it will use that. So now, instead of 244 milliseconds, the query takes 147 milliseconds. It's a modest improvement in Wormwood because its index is very inefficient. All it tells the query evaluator is which lines to look on, but that's not actually all that helpful. When you have a text file, the only way to get to line 4,783 in a text file is to go through the first 4,782 lines, so it doesn't help all that much. And, oops. Okay, so if you continue to be interested in database technology, I would encourage you to check out the Wormwood source code, which is on GitHub at this address. And also, if you have any deep database technology questions that you'd like to try out, you can find me at the Datalust Seek booth out in the main hall. And otherwise, does anybody have any questions from that presentation? Up the back?
I noticed that the data in the index was also sorted on the values of the index. What is your reason and the performance between having multi-column indexes and multiple indexes?
Sorry, what was the last bit?
Like having multiple indexes so that you will also have an index of the, let's say, the ages themselves, and also of a different sorting than the names. So if you sort by, have a query for names, but also for ages.
Yep.
So having two indexes, one for name and age, you have one for name with secondary multiple index.
Yeah. So obviously, you can build indexes that way. Wormwood, I mean, really, it's very minimal. It's not a real database. So the indexes can only be on a single field, and also actually the queries can only filter on one field as well. That's just how it is at the moment. But yeah, absolutely, you can have queries on multiple columns. And yep. There was another question. Yeah.
Yeah, but it's more or less the same.
Yeah.
Multiple indexes. How does it select, or how do you specify which one to use?
Well, that's the job of the query planner. So the query planner, it gets a data structure that represents our parsed query, and it has to come up with a plan for the best possible data flow graph. So there's all sorts of heuristics and things that it's going to use to work out the best way to do that. At some point, you get to a situation where the only way to do that is with statistics, because which index is the best to use is going to depend on things like how many rows are in a particular table, or what's the cardinality of a particular column in a particular table, and so on. So the query planner gets stuck with all that fun stuff. Yep.
So because it was only the text file, I was wondering if you did a version where you loaded the database into memory and then compared the performance without indexes.
I didn't. So I told someone before I started that I'd forget to repeat the questions. So the question was, did I do a version where the data set is in memory and compare the performance? I didn't do that. I usually work on Linux, and I'm presenting today with a Windows computer because my slides are in PowerPoint. And when I went to try out the demo on Windows, the performance is just completely and utterly different. And I think the reason why is actually like the printing of the rows in the console. I think that's the slow part. So I guess it's hard to know where your performance bottlenecks are. So I didn't. Well, previously when I've given this presentation, I've demonstrated the select from the entire table, but I didn't use this example today because it takes ages. But on Linux, that's like 100 milliseconds or something. So it's hard to know where your performance bottlenecks are. There's all sorts of problems with performance in Wormwood. So when it goes to use an index, it has to read that index file and parse it as JSON, which is just a ridiculously slow thing for a query executor to want to do in evaluating a query. But that's not what it's for. Yeah.
You explained that the speed up that you got from using the index was limited because the system has to sequentially scan the file, the text file. Can you explain how a real RDBMS overcomes this?
Yep. So depends on your real RDBMS, but the general solution, I mean, I've never built one. As I understand it, the general solution is that an RDBMS knows how big a row is. So if you know your starting point in memory, you know the size of a row, then you can jump. It's an array lookup, essentially. And this is why the database engines force you to specify the size of the column. If you want to store text, you have to say I'm storing 20 characters of text. And it's always going to take 20 characters, regardless of what the actual size of your input is. Yep.
Sometimes we find ourselves have to rebuild our indexes.
Yeah.
Because performance is too slow. But we can't seem to identify the perfect timing to do that. Is there a rule of thumb to use?
I honestly have no idea. Yeah. I guess when the server's not busy doing other things, that's available capacity, so it doesn't matter how long it takes if it's not doing something else. It's the best I could think of. Okay, thank you.